We are going to look at change of variables. In multiple integrals. Which is actually an interesting topic. Now, let's begin with the UV plane, a departure from what we have been doing. Okay. And we have a region here. We are going to look at n equal to first. And later on, we are going to look at the case when n is equal to 3. So we have a solid here, a region here. Okay. And we are going to look at the corresponding xy plane. Okay. So we have a region here. Let's call it S. And we have another region here. Which we call capital R. Okay. Now we are interested in double integrals on this region R. Okay. It may be a complicated integral. So we want to change coordinates. We want to change variables to make the integral on this region R more tractable. That's the idea. Well, the whole idea is to change coordinates. Okay. So I am going to suppose that there is a mapping from the UV plane to the XY plane. from the region S to the region R. And the mapping is given by this equation. Where X is a function of U and V. An arbitrary function. I still remember during the test, one student sent me an email saying that the question 1 is wrong and the question 5 is wrong. Because he said that there is no function for F. Well, here I mean an arbitrary function G. Okay. When a formula is not given to you, we mean an arbitrary function. And Y is another arbitrary function. H of X, Y. Okay. And we assume that this region is completely mapped onto this region R. In other words, R is the image of S under this mapping. Okay. Now we are going to look at a nice rectangle. Inside the region S, grown up from a point inside S, as before. Now, this rectangle would be mapped into a certain region, small region, inside R. Okay, so let's say is something like this. Okay. All right. Now, let me try to magnify this. Otherwise, the figures will look very messy and also ambiguous. Okay. So I am going to magnify a rectangle. This is the UV plane. And this is a rectangle. Okay. It's actually a very small rectangle, even though it looks big. Now, let me call this point U0. V0. And then the length of this base here is du. An increment in u. So this point would be u naught plus du and the second coordinate is v naught. Right? Now, if you look at this point here, let's assume that there is an increment in v, dv. So the coordinates of this corner would be u naught and then v naught plus dv. I don't care about the coordinates of the remaining corner because I don't need it. Now, this is a very small rectangle. Okay. Now, it's mapped into a region in the XY plane. Okay. This is X and this is Y. Okay. Then what happens? Well, of course, after this transformation, this rectangle will be distorted into something like this. Say, okay. Well, again, this is a very small region. Okay. Now, I am going to look at two vectors. This is one vector. Okay, joining these 2 points. And this is another vector. Joining these 2 vertices. So I have another vector. All right. So let me write down something. So we let X be G of U and V. And Y is H of U and V. Okay. Then the region S to begin with is mapped onto the region R at the beginning. Okay. And we actually assume that the region R is the mirror image of the region S. And then I look at a small rectangle associated to this point in S. Okay, so this is ds. And this is dA. For the region R. Okay. Now, it's very easy to calculate ds, the area of the rectangle. It's just du dv. But for this one, it's not easy at all. So our first job is to find a formula for dA. Okay, so you see, these differentials are the heart of the matter in integration. Okay. Now, let me introduce another notation. Okay. I am going to introduce the vector R, which is x times the vector I plus y times the vector j. Okay. Now, here observe the following thing. Let's say that this point is mapped into this point. The point here is mapped into this one. And this point here is mapped into that. Okay? By this pair of mappings. But this pair of mappings is encoded into this vector. So well, I don't know what to call this vector. Let me not call it anything. more names there are, the more confusing it is. So let me simply say we get two vectors. We get this one, the longer one first. So as I said, this point is the image of the point which I have just erased. So we get R at what? Well, if you remember, this is going to be U naught plus BU. And V naught. So in order to get this vector, we take the terminal point and subtract the initial point. The initial point came from the original point, U naught, V naught. And then I am going to look at this vector without naming it. So it's the endpoint minus the initial point. The endpoint here actually came from the corner up here of the rectangle, which is U naught V naught plus EV minus this point. And this point is the original point, U naught, V naught. Good enough. So what are we going to get? We get this vector, we get this vector, right? But before calculating dA, let's simplify this. They don't look like nice to us. Now, can anybody tell me what to do with this one? V naught is unchanged. And U naught has been increased or decreased. What to use? We have done that before.
Partial derivative.
Take the partial derivative. But more precisely, what is it?
For U.
Are you using?
So partial derivative for u,
No, the partial derivative with respect to u. At some point between u naught and u naught plus du. What theorem is that called?
mean value theorem.
Mean value theorem. That's correct. So we are going to have the following. So we are going to take the partial derivative of r with respect to u, since the u is very small. Then the point between u naught and u naught plus du is very close to u naught. So I am not going to write that down. And then you have du. This is the mean value theorem. Right? Now, similarly, you can do the same thing. So is the partial derivative with respect to v evaluated at u naught v naught, which I am going to omit, and then dv. Du and dv are numbers. So you have a scalar multiple of a vector. The same here. In other words, this vector is Ru du. And this vector here is Rv dv. Right? Now, actually, these two vectors determine a parallelogram. Right? You can complete it. And because everything is very small, dA is very small, du is very small, and dv is very small. So this dA is very much the same as the area of the parallelogram spanned by these two vectors. So dA the area of the parallelogram. Let me just write it like this. I don't want to write down the whole word. The area of the parallelogram spans by the two vectors. By Ru, du, and Rv, dv. But how do you find the area of a parallelogram spanned by two adjacent vectors? Anybody? I think that's nothing new. You have two vectors. You have a parallelogram. You want to find the area of the parallelogram. What do you use? You use something that one professor said is useless in mathematics. Does it ring a bell? The cross product. He said that he cannot see the role of the cross product in mathematics. All right. So we are going to find the area. Actually, that comment was made nearly half a century ago when I was 20-something. Okay. But some comments are so impressive, okay, that you can never forget. Okay, so what is EA? Then EA is going to be the cross product of this vector with this vector. Actually, the absolute value, because it has to be positive, or the length of the cross product. Okay. But it's not good to leave the answer like this because it's difficult to work with it. So we have to simplify this. So what is it? It's the length of the cross product, right? So I am going to have I, J, and K. This is vector integral calculus. And then I am going to have what? Well, we have this one and that one. So what are we going to get? What is RU? R is x uv, actually g of uv, but you can write it as x uv. Times I plus y of uv times j. Okay. So the vector RU is going to be dx du times I. And j is dy du. And there is no k. So it's 0. And then I am going to look at RV. So it's going to be dx dv. And then dy dv. And 0. But in calculating cross product, we use a determinant. And then you are going to take the length, right? Well, today is very quiet, no questions. Now we are going to multiply out the determinant, which is 3 by 3. Simple enough. So we have 0, we have 0, and then I have k times what? Then we write down two columns. For calculations. So 0, 0, and then I have dx, du, dy, dv times k. And then you have to multiply in the opposite direction and subtract. Only one term survived. Minus dx dv dy du times k, which we expect already. The cross product is a vector perpendicular to the plane determined by the two vectors. Okay. So after all this, what are we going to get? So we are going to get the following. It's going to be dx du dy dv minus dx dv and then dy du. These are numbers. So I take the absolute value and I have to take the length of the vector k. What is it? What's the length of the vector k? 1.
1.
So that's all we get. But what is this? This is a determinant also. Oh, by the way, I forgot du dv. They come out. Right? Now, these partials form a determinant. Well, a 2 by 2 determinant, which is easy to remember. Is dx du dx dv dy du and dy dv. And then I have this du dv. That's dA. Right? All right. So dA is equal to this. So now I am going to take a function. An arbitrary function with no formulas. So let's assume that is continuous. On R. Then I am going to look at the integral, the double integral on R. Now, here I also want to make a comment. In the test, a student said that question 1 and question 5 are wrong because this integral has no range. Well, a double integral is actually given on a region, right? And I have given you the region.
It was technically in R3, so it's technically they're bounded from -infinity to infinity, but then we have to work around.
They are
With the-
all minus infinity to infinity, minus infinity, minus infinity. Right? You don't have to figure that out. That's R3. But then you have to use polar coordinates and you have to figure
Yeah,
it out. Okay? Cylindrical coordinates. As I said, you have to set it up. Yeah. It's certainly not given. So this integral then is, well, this may be very complicated to do. But after this change of variables, well, time is almost up. So it's the integral on S of G of UV, because that's X. And then H UV and then I have BA. But I am going to write this in the following form. And what is this? Where this symbol here, a very convenient symbol. Is this one. And this is an extremely important quantity in vector integral calculus. And it's called the Jacobian. Today is not too bad. Not too much overtime. Or is it overtime? Or 1 minute overtime? Okay. And it's very symmetric. So there's no way you can forget about it. So again, you see again and again, the differential is the crucial part in integration. And then once you have the differential, you have to set up the endpoints, the range. Okay. By the way, the test is quite easy. Well, maybe number one.
I found question 1 from the textbook. It was a textbook question.
Oh, really?
Yeah.
I never read the textbook, maybe. Yeah, so what is the answer?
It's just putting the X and Y inside as well.
But
Pretty much.
what's the answer?
Hold on 1 sec.
It's the angular momentum. D by d theta.
Yeah.
Right? So all these questions are very meaningful. And then for the R3, what do you get for the answer?
Pi root pi.
Well, root pi to the power 3. So it's pi to the 3 halves.
It's the same thing, right?
It's easy, right?
It's the same thing as pi square root of pi.
Well, one of them is square root of pi.
Yeah.
You can take the set integration out.
Yeah.
Then you use polar coordinates.
Mm-hmm.
And that's how to do it. The question is certainly not wrong anyway. And we actually did something like this for R2.
Yeah, we did something from minus infinity to infinity of e to the power minus x squared.
Yeah.
And
But
like from
we need to calculate this. And then we use polar coordinates. A double integral on R2.
Yeah.
I just want to test understanding without a lot of computations.
And then from 0 to infinity, it's just half of square root of pi. So
No, 0. That's the
0 to infinity, right? So that's like half of,
polar coordinate, yeah, cylindrical coordinate.
yeah.
Okay, so seems that you did well.
I only made like a few tiny mistakes. Like I think it was like in question 3, I put 3 instead of a 5 for one of the,
What's question 3?
it's the gradient.
You mean the directional derivative?
Yeah, I made like a small error. Is that like I put like a 3 instead of a 5, so the rest fell off.
Well, if the method is right, there won't be too many marks taken off.
Okay.
Hopefully you can get this back next week because I still haven't made up the solution and the grading scheme because I have to make this up for another course, which is more difficult.
Professor, do you know when you'll be able to release the solutions for test 2, just so that we can see how the questions should have been done?
I will post it certainly this week because you are going to have the test back next week. So
Thanks.
when I send the answers to the TA, I will send it to you too. Okay,
Yeah, thank you.
Professor,
yes,
on Cengage, there's no WebAssign 8.
no. I think I said last week, during the test, there won't be any WebAssign, but there will be one more, and then that's it.
Okay, thank you.
Yeah, I will give one more this week. And then the course is finished. Well, except the final. Do you know when the final is? I haven't checked it.
It's on I think it's on Thursday, December
Okay, what is
18th,
18,
16, I mean, sorry.
16, okay,
Yeah, it's in the morning at 9.
okay. Yeah. I have another one on the 17th. But it's all right.
Do we have to join Zoom
Yeah,
during the exam?
yeah. Well, it's
Okay.
a e-class, but have you heard about that? There will be no invigilation whatsoever nowadays.
What?
Have you heard about that?
No, I don't
No.
know what that means.
No invigilation, no Zoom invigilation, no proctoring, and so on.
Oh, okay.
Starting winter.
Okay.
Actually, I started this a long time ago.
Well, aren't we going back in person? So it wouldn't matter anyways.
Pardon me?
I said, aren't we going back in person starting next semester?
Yeah, in person. And I heard that if you haven't, or if you cannot present any proof of 2 vaccination, you are not allowed to enroll in any courses. So make sure that you do this. Okay. And even if you have taken 2 vaccination, if you don't upload a proof to the university, you are also not allowed to enroll in any courses. Yeah, because this term, I think it's a mess anyway.
Are you teaching next semester?
I am not teaching next semester. I have taught too much. But I will teach in September.
If the cases go back up, do you think they will revert back to online classes?
Well, if things suddenly go worse,
Okay.
then we are back to online. Well, it's possible. It's possible that things suddenly go worse. Well, I hope not, but that's only a wish. Yeah. Okay. All right. So see you on Wednesday. So you seems to be doing quite well anyway. Maybe open books are easier. But some courses are not, even open books, they may be difficult. Okay, then see you on Wednesday.